in terms of what we know about our Cartesian plane, I'm not going to like do a full on like, you know, like starting from the beginning with trig. So I'm assuming that we understand where the reduction formula and stuff have come from. However, what we need to sort of know is what happens in each quadrant. Okay, so we have 4 quadrants on our Cartesian plane. We number them from top right anti-clockwise. So that's quadrant 1, 2, 3, and 4. So when I talk about quadrant 3, we know where we are, for example. And in each case, something different is happening to each of my trig ratios in each quadrant. Now remember, when we draw or when we are working with trig on the Cartesian plane, we have a specific coordinate x, y, and whatever the length from the origin to that point is our r value. And so we've got our trig ratios that we can now go and essentially work with. So sine, and remember your angle from your x-axis to the line is your reference angle, or theta, whatever you want to call it. So sine theta is equal to y over r, cos theta is equal to x over r, and tan theta is equal to y over x. Now, grade 12s, I've said this to you before, you don't need to work with the y and the x's and the r's if you're not super comfortable with it. You can still kind of imagine the triangle and go from there, but these are ratios. But what now happens when we move into quadrant 2 is the x value is now negative on the negative x-axis. So sine remains just y over r because y is still positive and the radius is always positive. However, cos becomes negative x over r, and tan becomes y over negative x. This is why we say in quadrant 2, sine is positive, and this is where the cast diagram comes from. Okay, so all of my ratios are positive in quadrant 1. Sine is positive, and then I go and circle cos. Sine is positive in quadrant 2, and if we keep writing out our ratios, we get where the rest of our ratios are positive and negative. Okay, I'm not going to do that, but you get the picture. So that's where cast comes from. Now, cast is super useful to us because when we do now talk about our reduction formula, we understand where ratios are positive or negative. So your reduction formula is basically how we can go and work back to the original acute angle that formed our reference angle, and how we can then work with our ratios from there. So quadrant 1 will be an acute angle, so that's just theta. But quadrant 2, if I took this blue line that I had already drawn and I reflected it over the y-axis, it now sits over there. Okay, that's a perfect reflection over the y-axis. We now have negative xy. And so what now happens is if I wanted to go and measure the angle from the x-axis to that line segment, I can use my geometry thinking. If I went all the way, and remember this angle over here is a reflection of theta, so it's the same size. This obtuse angle would be 180 degrees, so the straight angle, minus the theta would give me the obtuse angle. Hence why my reduction in quadrant 2 is 180 minus theta. And so if we keep going with these reflections, we get our reduction formula. So quadrant 3, 180 plus theta, and quadrant 4, 360 minus theta. So that's where our reduction formula comes from. It's all just like reflections, essentially. All right, so when we go and have a look at our Cartesian plane, our reduction formula, incredibly, incredibly important. Another thing that is also important is understanding what happens with your co-ratios. Okay, so co-ratios that we work with are 90 plus and minus. You do have 270 that you can work with. Some teachers teach it, some teachers don't. Personally, I don't ever work with 270. It's just adding more confusion to a section that already sometimes is a bit tricky. So I only work with 90 plus or minus. Like I say, there are 270s. It's not actually in the syllabus anymore. It's not like examinable. You can use them, but not something we're going to focus on. So 90 plus or minus. If I go 90 minus, so here's my 90-degree angle at the positive y-axis. 90 minus are all my ratios in quadrant 1. And so this is why if we've got cos of 90 minus theta, I still have a positive sine theta. So the co-ratio is still positive because we're in quadrant 1. Same as 90 minus theta is still cos theta because we are still in quadrant 1. However, when we move to quadrant 2, okay, we need to be careful because in quadrant 2, sine is positive, but cos is negative. So when I go and work out cos of 90 minus theta, 90 plus theta, what ends up happening is cos in quadrant 2 is negative. So my co-ratio is negative sine theta. Sine of 90 plus theta, sine is positive in quadrant 2, so it's positive cos theta. So we just need to be very, very careful in which quadrant we're working and what that means about our trig ratio. Right, before I carry on, can I book you?
So, ma'am, the 90 changes the ratio.
Exactly. It changes our ratio.
Okay.
So guys, it changes your ratio because if we just go back to sort of a very basic situation that we have here. Come on, you silly thing. Okay. Oh, okay, we're going to draw a better right angle triangle than that because, let's get it right. So let's say, for example, I had this right angle triangle that was fighting with me, and this was my angle theta. This angle through sum of angles in a triangle is 90 minus theta. Okay, so that's just basic geometry. If, for example, I went and wanted to find sine theta, okay, so here's my reference angle theta. This is the adjacent side, the opposite side, and the hypotenuse. Sine theta would be opposite over hypotenuse. However, when I now go and find, let's say, for example, cos of 90 minus theta, what I'm doing is I'm changing my reference angle. My reference angle is now up here. And so this is now my opposite side, and this is now my adjacent side. So they swap. So cos of 90 minus theta would be, where am I at? Opposite over hypotenuse. Sorry, it took me a second. And what we end up seeing is that those ratios end up being exactly the same as each other. Right, so this is why the ratios swap from sine to cos and from cos to sine, because when we change our reference angle, because of the swapping of the opposite and the adjacent, we actually end up getting the same ratio for both of them. Okay, so that is the basics of your Cartesian plane. There was something else I wanted to say about the Cartesian plane, but obviously not. Oh, right, so that is the basics of your Cartesian plane. The only other thing I wanted to say, which obviously took me a second to remember what it was I wanted to say, is negative angles. Because for some reason we get stuck with negative angles, but negative angles. And Rato, I do see your hand, just give me a second. So positive angles are always measured from the positive x-axis anti-clockwise. If we had measured an angle clockwise, so if I measured an angle from my positive x-axis down clockwise, this is a negative angle. And what happens is we're then sitting in quadrant 4. So when we are working with negative angles, again, take into account which quadrant we're in. Because we're in quadrant 4, only cos is positive. So sine of a negative angle is negative sine of that angle. Cos of a negative angle is positive cos of that angle, because quadrant 4, cos is positive. And tan of a negative angle is negative tan of that angle, because, again, quadrant 4, only cos is positive. So just remember negative angles, quadrant 4, which ratios are positive or negative there. Right, Lorato?
Ma'am, can you hear me?
Mm-hmm.
Ma'am, for when you're doing like the side thingy magic at the top, why was for cos 90 minus theta, why is it opposite over hypotenuse instead of adjacent over hypotenuse? Even though I know they'll be the same value technically.
Okay, let's just see. No, listen, it's entirely possible my brain just had a bit of a brain fart. So let's just...
Oh.
No, listen. My brain. Okay, so let's just go back. Theta, this would be adjacent. This would be opposite. And if we now wanted, okay, so this is why. Because if we now want cos of 90 minus, this is my reference angle. The adjacent side is the opposite. And the hypotenuse is the hypotenuse. That's why. I had too many letters there. I do apologize. Does that make a bit more sense?
We still regard it as the same thing. We don't need to now swap the things around.
So that is technically what happens. But if you just change your reference point, this is why sine 90 minus and, oh, goodness gracious me. This is why sine theta and cos 90 minus are the same thing. Because when you now change your reference point to this angle up at the top here, the adjacent side is the original opposite side. So that's why we can say opposite over hypotenuse. Yes, you absolutely can say adjacent over hypotenuse, but then you can't see the relationship between the two as clearly.
Oh, okay. Now I get it. Thank you, ma'am.
Okay. Sorry, guys. Just let me choke a little bit and then I'll be back with you. Okay, so yeah, co-ratios. The name changes, and if it's cos 90 plus, sign change as well. Okay, but that is very basically our Cartesian plane. I found the Cartesian plane incredibly useful. I'll be honest, even like now, years later in my old age, I still draw the Cartesian plane whenever I'm doing trig. I still have my little cast diagram. I don't draw all of this stuff. I just draw cast and the quadrants. And every now and then I put in the reduction formulae. But for me, I still find this so useful. Okay, my brain needs to see it so that I know what I'm doing. So I'm just going to wait there in case you want a screenshot, and then we're going to keep going. Right, so guys, like I said, this all leads us into everything that we're doing. If you have a fundamental or basic understanding of trig and what's happening, we should be okay. Okay, so then a few other things that we just need to know in terms of our trig are finding the general solution. So we've spoken about these steps here before, so I'm not going to like go into them in detail until we do a general solution question. But just remember, general solution, first thing that you do is you isolate your ratio, then you find your reference angle, you decide on your quadrant based on the sign. And once you've decided on which quadrant you're working in, you're going to then apply the appropriate reduction formulae. Again, we will do a few general solutions, so we'll go through this again with actual examples. Apply appropriate reduction. All right, so general solution, just because they're not hard. Okay, there's like 4 or 5 steps that we follow in order to solve a general solution. But again, we make silly mistakes. So isolate your ratio, reference angle, quadrants, reduction ratios, solve, or reduction formulae, solve. That is it when it comes to general solution. All right, just your functions. I don't know why I chose not to leave myself space here, but we'll just pretend everything I do makes a lot of sense. And we're going to go from there. So Kani, there is another way, but I always used to do the other way. I think the other way is a little bit trickier, just because there aren't necessarily steps to do. When we get to a general solution, if you'd like me to show you the other way, I'm happy to do that. I just find general solution, because you've got steps in your head that you can follow, it is a little bit easier if you struggle with general solution. But there are other ways to solve trig equations. So I'm happy to show you when we get to a question like that, how else you can do it if you'd like. But like I say, for me, and if you struggle with general solution, if you follow the steps, then generally that is not more helpful, but generally it guides us better because we know what we have to do. I don't know if that made any sense. Okay, cool. All right, so when we get there, if you still want me to show you, I'm happy to. Just let me know. All right, guys, your functions. Like I said, can't tell you why I've made the choice to not leave myself any space here, but we're going to roll with it. So sine function, it's a wave. And we have 0, our maximum at 90, x-intercept at 180, minimum 270, and another x-intercept 360. So this is our sine graph. Cos graph, Okay. Okay, it wasn't the best cost graph in the world, but it doesn't matter. Maximum at 0, 1, x-intercept at 90, 0, minimum 180, negative 1, x-intercept 270, 0, and then another maximum at 361. Okay. Tan graph, not the nicest graph in the world, as we all know. I'm just going to do it down here. Tan graphs, what we need to remember is that we have asymptotes. So we have an asymptote at 90 degrees. I'm only drawing the positive 360. Obviously, these graphs go on to infinity. And 270. Tan graphs look something like, oh, not like that. So let's try that again. It didn't really get better, but we'll just pretend. And guys, remember, one of the really important points here is this point at 45 degrees 1. That helps us figure out our amplitude for a tan graph. Now, I've hopped on about it before to you guys. I'm going to say it again. Knowing your parent functions of your trig graphs makes your life 1,000,001 times easier. So in those info packs that I put on Google Classroom for you guys, I have done a way more detailed summary of your trig functions for you, outlining all the different manipulations that we can deal with. So I would definitely go and have a look at those. But at the end of the day, grade 12s, if you know your parent functions, you're making your life 10 times easier. It just means that you can go and compare how things have changed from what you know the original is, and you can understand, has it shifted up or down? Has it shifted left or right? Is there a period change, etc., etc.? Okay, so knowing your parent function is super important. And like I said, it is in that info pack that I put on Google Classroom, I want to say last term. So please do go have a look at that. But genuinely, parent functions, it is, for me, the easiest way to do trig. Otherwise, you are just trig functions. Otherwise, you are just overcomplicating it for yourselves. Right, 3D trig I'll get to in a second because we've got the rules there on the right-hand side and I want to chat about those rules. But then, as I said at the start of the lesson, trig, especially at a grade 12 level, is all about applying formulas. So whether it is your deduction formulae, whether they are your identities. So remember, the identities that you learned in grade 10 are your square or your Pythagorean identity, which is this one up here, and then the manipulations thereof, as well as your tan identity. And in grade 12, we learn about our double angle formulas or identities and our compound angles, all of which we obviously need to be able to use. But remember, all of which, so these double angle and compound angle formulae, they are all on your formula sheet. The only ones that are not on your formula sheet are your Pythagorean or your square identity and your tan identity. You need to know those. Okay, you just have to know them. They're not on the formula sheet. That is something that you have to remember. Kani, I'm not too sure what you mean. If you just let me know. Like proving a trig identity. Is that what you mean?
Ma'am, like, I don't know. It was a question, and then like our teacher said it was one of the proofs that we had to like know, or like you had to prove a compound angle. Yes, like one of those things.
Okay, with you. I think we actually did one of those when we did trial prep.
Okay, I wasn't in those lessons, but I'll check.
No, it's fine. I've got it all here. Obviously you're just making me doubt myself now, so it's cool. Yo guys, sorry, I've taken a tangential moment here. So what Kani's asking, hang on, let's see if we can find it. No, it won't be this lesson, it'll be this lesson. Yeah. Yes. So we did this when we did our trial prep. So you can go and I'll double check. You can go and prove your compound angle identities using, no, it wasn't this question. Obviously, now I'm doubting myself. Okay, I know we did one. Let me look for it. I know we've done one. If we haven't, it'll be in the information booklet because of the specific thing that we spoke about. But I'll get there in a second. Okay, so Kani's asking about proving your compound angle formulae, which you definitely can be asked to do. It comes up a little bit more in trials than it does finals. But essentially what you will be asked to do is you will be given one of these formulae. So say, for example, I will give you this cos expansion, and then I'll ask you to use it to go and prove the sine expansion. All you're doing there is you're using your co-ratio. So this is why I say to you earlier that your ability to understand the basics, particularly of trig on the Cartesian plane, is so useful, because as you can see here, we need to go from cos A cos B to sine A cos B. The only way to do that is to use a co-ratio. So we're using a whole bunch of co-ratios to do it. I know we've done a question like this, and if I can't find it now, I will find it before Wednesday and just go through it again with you guys. But like I said, it doesn't come up a whole lot in finals, definitely more in prelims. But maybe, see, now you set me off. Maybe when we went through trials. Haha, I knew we did it. Okay, sorry. Right, there we go. So that's exactly what I said. So we've been given the cos compound angle formulae, and we then had to use it to prove the sine compound angle formulae. And all we're doing there is we're using co-ratios. So I'm happy to go through one like this again. We'll see how far we get today. Otherwise, I will do a question like this again on Wednesday. But it is, as you can see here, it's all about using co-ratios to change real causes to sines and sines to causes. But like I said, we can definitely have a look at that if you still want to. It's, like I said, it doesn't come up a lot in finals, definitely in trials, but it is there. But we can definitely do that. I knew we had done it. All right, so that is your double compound angle formulae. And then the last little thing that I just want to mention, guys, are your 2D trig formulae, which are these bad boys over here. Now remember, this is all on your formula sheet. So this is a screenshot directly from your formula sheet. And the only thing I want to say about the 2 and 3D trig formulae is that don't get hung up on A, B, and C. So A, B, and C is basically your labels of your triangle. So let's say A, B, C. The lowercase letters are the sides opposite those angles. So that would be side C, side B, side A. And all they indicate to us are sides and angles. So for example, okay, if I look at my area formula, it says half AB times sine C. So there's A, B, and here's angle C. All that says to me is I must take half, 2 adjacent sides product. So I don't have to have AB. I could have BC. I could have AC. As long as they are right next to each other, and then sine of the angle in between them. So don't get hung up on the A's and the B's and the C's. Understand what it is saying to you on a basic level. So like I say, the area rule is saying half, 2 adjacent sides, and the included angle. So as long as you have that information, 2 adjacent sides and the angle in between them, you can find the area. It's the same for the cos rule. So the cos rule, if again you have a look at my beautiful diagram, and it's just the contrasting color here, it says a squared, so here's a, is equal to b squared times, or plus c squared, minus 2bc, so the same two sides, and then cos of angle A. Angle A is my angle opposite the side I'm looking for. So that's exactly what we need to say. So the wanted side, or unknown side, I don't know why I said wanted. That was a weird description. But anyways, we got their name. So it's your unknown side, cos of the angle opposite the side unknown, or your unknown side. Again, I'm phrasing things very weirdly, but anyways. And B and C are your two other sides. And so we need to start understanding these rules sort of at like a basic level, not in terms of ABC, because I don't necessarily have to give you a triangle labeled ABC. I could give you a triangle labeled XYZ or MNP or whatever the case is. And we don't want to then get tripped up about what the rule actually tells me to do. Okay, but obviously we're going to practice all of these things, so don't stress about that. But just understand that when it comes to 2D trig, understanding the formula, it's the same as functions. Understanding the basic formula, understanding the basic trig function is very helpful to you. All right, so let's take a screenshot, and then we're going to have a look at all the types of questions you can expect, and then we're going to have a look at some examples. And like I say, in terms of that compound angle proof thing, I'm happy to do a question like that again. I'll put it in for Wednesday if you would still like me to do it. Okay, so let's see what types of questions we can expect in trig. Right, trig generally consists of about 3 questions. Just scrolling here. So you get a basic sort of ratio question. It's either on the Cartesian plane generally, or it's a question where we say like cos of 15 degrees equals P, and then find these ratios in terms of P. So it's just a basic work with the Cartesian plane, work with a triangle, give me some ratios. You'll then be asked to simplify an expression. It's those fun ones with all the reductions and co-ratios. So sorry, reductions, co-ratios, generally it's a fraction, something like that. You'll be asked to prove an identity. This is where general solution can come up. So let's put a little star here. This is where general solution can come up, particularly when asked where is the identity undefined. And I think I actually have a question like that we'll have a look at. Trig functions. This is also where general solution can come up with points of intersection. And this is generally where we test general solution. So you can see here, I haven't listed general solution as a type of question. It falls into one of these other 2 generally. And then finally, you will have a 3D trig question. So these are generally questions 5, 6. This will be question 6. This will be question 7. So you get 3 questions on trig, kind of broken up into those: general trig, trig function, 2D or 3D trig. The 2D, 3D trig generally is not worth like a lot of marks. I would say between like 6 and 9 marks. If you think of that in the totality of trig, which is 50 marks, not a lot. The bulk of your trig comes in about, I would say about 30-ish marks, comes in with these first 3: simplifying basic ratios, simplifying expressions using reduction, proving identities, and working with that sort of stuff. So that's what you can expect for your trig in paper 2. Again, if you want to take a screenshot of that, you can. And like I say, the general solution doesn't come in with a general trig where you expect it to. It often comes in with proving identities and trig functions with points of intersection. Right, just back to Connie's question. So Connie's question was about the proof of the compound angles. The proofs of your 3D trig formula, so area rule, sine rule, and cosine rule, technically are examinable as well. I can't remember if I put them on Google Classroom. If not, I will. They are very easy. Technically, they are examinable. And there are proofs like your Euclidean geometry proofs where you have to add a construction and all of that sort of thing. I have not seen it asked. Whether that means they probably won't ask it, which that is my gut feeling, or whether that means, oh, let's mix it up. Let's ask a 2D trig proof question. I don't know. My gut says no, because generally speaking in paper 2, the proof is coming in the Euclidean geometry, not in trig. Yes, in compound angle formulas and stuff like that, but not a proof in terms of the 2D or 3D trig rules. So like I say, technically it is examinable. They're very easy proofs. I definitely have them somewhere, which I'll pop onto your classroom. But 3D triggers are really considered the complex problem solving question. I really don't think they'll ask the proof. It's a pointless question at the end of the day. All right, but let's get into it. So I'm assuming we screenshot it because now I've rambled. Let's have a look at some questions. Right, remember, if at any point you have questions, please ask, and I will obviously stop and help you. But let's get into it. So guys, this is the first type of question. Like I said, it's your basic ratio type question. Now these questions, again, not hard in any shape, sense, or form. Where it trips us up is understanding how the angles relate to each other. And why do I feel like I typed something wrong? No. Okay. So we have been given cos of 11 degrees equals k. Determine the following in terms of k without using a calculator. Now, grade 12s, this without using a calculator, fine, great. But whenever I'm given something like this question, where I have an acute angle is equal to a variable, excuse me, or even something like a Cartesian plane situation. So where they tell me this is the ratio for sine and we're between 180 and 270 or whatever. Draw a diagram for yourself. Okay, it doesn't have to be a perfect diagram, but draw a diagram so that you can see very clearly what it is that you're working with. Now, because this is an acute angle, I'm happy that I can go into a right angle triangle. And obviously, remember, trig, right angle triangles. We've got our 11-degree angle. And then using sum of angles in a triangle, I know that my other angle that I have here is, that's embarrassing, 79 degrees. Yes, 79 degrees. My brain just stopped working there. Okay. Now, because of this information given to me, I'm going to use the 11 degrees as my reference angle. And remember, cos is adjacent over hypotenuse. This k could be written over 1. So the adjacent side to 11 is k. The hypotenuse is 1. And we can then use Pythagoras to work out the missing opposite side. So just so that you can see the Pythagoras calculation, you can write it down immediately, but just so that you can see it, it would be the hypotenuse squared is equal to my opposite side squared plus my adjacent side squared, which is k squared. We then want to solve for the opposite squared. So that would be 1 minus k squared. And obviously we don't want squared, so the opposite is equal to the square root of 1 minus k squared. Again, you do not need to write all of that working down. I'm just showing you what it would look like if you did. You obviously can, especially if you're not super comfortable with just being able to get that answer in your head. That's absolutely fine. But we do obviously need that third side of our triangle. So now that I have all of this information, I can now go and have a look and see how I can answer these questions. So first question of sine 11 degrees, that's nice and easy. I have my 11 degrees. I've just worked out my opposite side. That's over the hypotenuse, which is over 1. So technically, you don't have to worry about the fraction. And sine of 11 is 1 minus k squared. And so we have got our first 2 marks nice and easily. But because I drew my diagram, again, please draw a diagram. It honestly just makes your life so much easier. Okay, you will thank yourself later for drawing your diagram. And like I said, even if it doesn't say, draw one. Right, this is now where things not start getting complicated, but where things start ramping up a little bit. We now need to understand where the angles come from. Sorry. So question, why would it not be opposite equals 1 minus k instead of opposite equals 1 minus k squared? Because remember, you're squaring, it's Pythagoras. So Pythagoras is side squared. You also can't square root separate terms. So if this had been, for example, 4k squared, square rooted, then you could say 2k because that's one single term. But these are 2 separate terms. We cannot apply the square root to separate terms. It has to be to a single term that we apply the square root. Kani? Kani, do you have a question? Okay, cool. All right, so guys, now we get into a situation where now we have to think very carefully about where this angle comes from. So sine of 22 degrees. Obviously, first things first, check if it's an angle in your triangle. It isn't, because we've got 90, 79, and 11. So now we need to think a little bit deeper. So have a think, where or how do you think we can get sine of 22 degrees? How can we use the angles we've been given, 79, 11, and get to 22 based on what we know within trig? Okay, so my first thought would also be reduction. My last thought would be correlation, but my first thought is always to check reduction. So if you're going to go reduction, just go and have a think of, can you say 180 minus 79 or minus 11 to get 22, or 180 plus one of those two angles, or 360 minus? So can you use reduction to actually get an angle of 22 degrees? Leila?
Hi, ma'am. Ma'am, I didn't want to answer. Sorry, I just wanted to ask. But the first question, was it what is it, an all or nothing question, or do we have to include the
I will
workout?
show. Yeah, I'll show the mark allocation now in a second, but you do get a mark for working out the opposite side, so doing the Pythagoras, and then you get a mark for the answer. Yes.
Okay, thank you, ma'am.
Sure. Okay, guys, this is a double angle. If you took 11 degrees, which is in your triangle, and you times it by 2, you get 22 degrees, double angle. So what we can do is we can take this and we can expand this. Now, the sine double angle rule is that sine of a double angle is equal to 2 times sine of half that angle times cos of half that angle. And now we have an expression in terms of the angles we have in our triangle. So sine of 11 degrees, we just worked out in 511. That was root 1 minus k squared. Cos of 11 was given to us originally. That was just k. And if we go multiply all this together and just simplify, we get 2k root 1 minus k squared. So look out for double angles. Look out for reduction, co-ratios, compound angles, etc., etc. All right. So based on that, and based on what I've just said, cos 19. 19 is not an angle in my triangle. So I want you to think carefully about how we could potentially get 19. Is there an option for a co-ratio, a reduction, a compound angle? How can I get 19? And it's 3 marks, so it's going to be a fair bit of work that we're going to have to do. And I'll give you a hint, compound angles. I can give you more of a hint, but I'm going to start with compound angles. Any ideas? Oh, great tells we need to practice trig. Okay. Nice, Awami. Okay, we definitely could use that. So Awami's gone 79 minus 60. 60 is a special angle, so that works. 79 is the other angle on my triangle. That works. I'm going to go with that. I would have gone 13 minus 11 because that also gives me 19. But let's go with yours because you gave me an answer. So if we take, let me just get my brain working here properly. If we take cos of 79 degrees minus 60, 79 minus 60 gives us 19 degrees. So we get the angle that we want. And now, whilst this is not great, we can go and expand this according to our compound angle formulae. So cos compound angle is cos, different sign. So in this case, plus, and then sine. So cos 79 times cos 60 plus sine 79 times sine 60. And all we do now is we use our special angles. Now, I am absolutely horrendous when it comes to special angles. It is not something I know, nor something I choose to want to know off by heart, which I know is shocking. Where have we got? Cos 60. Okay, so cos 79, you go to a triangle and you read it off. Cos, adjacent over hypotenuse. So this would be the 1 minus k squared rooted. Cos 60 is a half. Plus sine 79, opposite over hypotenuse, that's just k, times sine 60, which is root 3 over 2. Every now and then I do know them, root 3 over 2. And now we just go and simplify this beautiful mess that we have here. So when we go and multiply this first term over here, we get the square root 1 minus k squared over 2 plus root or k root 3 over 2. Those denominators are the same, so we have an LCD. So we've got k root 3. I don't know why I went that way. Let's try again, sorry. So I've got root 1 minus k squared plus k root 3 all over my LCD of 2. Okay, not the nicest looking answer by any shape, stretch, or form. But we have gone and worked with the angles we've been given. We have found an expression in terms of the angles I know I have and I know that I can work with. I have then gone and applied or expanded my compound angle rule, and I was able to then substitute in what I know. Now, you would get exactly the same answer if you had gone the other way. So like I said, I would have gone cos 30 minus 11 degrees. You get exactly the same answer. So it really makes absolutely no difference. But again, guys, be thinking about double angles, compound angles, and anytime they say without a calculator, kind of have special angles somewhere in the back of your head. Okay, so I'm not going to go through it step by step again. I'm just going to run through our thought process. So, whoops, sorry. So we knew that we didn't have 19 in the triangle, so we needed to find another way to get 19. 19 is not a double angle of 11 or 79, so that rules out double angles. I can't use co-ratios because 90 plus or minus 79 or 11 doesn't give me the 19 degrees that I want. And so now I need to think, what else do I have? I've got compound angles. So then my question is, what two numbers could I add or subtract together to get 19? Now, obviously, there's an infinite number of possibilities. But the key here, like I said, is it said without the use of a calculator. And so think special angles. So Owami said, well, let's go 79, which is an angle in my triangle, minus 60. Gives me the 19 degrees. Special angles, you know the ratios for. 79 is in my triangle, so I can read the ratio of my triangle. And so I'm able to simplify. Like I said, it's not the only way to do it. You could have gone cos 30 minus 11. 30 is a special angle, so you know the ratios. 11 is an angle in the triangle, so you can read the ratios off your diagram. And so you can go and simplify. So, like I say, think in terms of, this is like my order of thought process. I start with, is this just a basic reduction? Can I just say 180 plus or minus or 360 minus? If I can't do that, then I go to, is it a double angle? If I can't do that, then I go to, is it a compound angle? Particularly with special angles. If it still isn't any of those, then I go to co-ratios begrudgingly, but generally speaking, it'll be one of those three somewhere along the line. So I hope that makes sense, Rato. Cool. And then guys, once you do have your compound angle thing, obviously you just expand it so that you can get each of those ratios that we spoke about. Alrighty. So 514, a little bit trickier. It did take me a second to like wrap my head around it. So I see Kani's got a question which I'm going to answer. All I want you to do right now is think how this 5.5 degrees relates back to an angle that we have in a triangle. So think reduction, think double angles, think compound angles. Kani?
Ma'am, can I ask, so in this question, the one we did now, we had cos 79 minus 60. So when we're doing that, do we have to use like an angle that's within our triangle, or can we like look for different numbers to give us 19, or must it be in the triangle?
It must give English. It must be in the triangle, because remember, we are trying to write down the ratio in terms of k. So I'm going to have to use one of those angles in my triangle so that I can introduce the k.
Oh, okay. Thank you, ma'am.
Okay, but yes, exactly. We want to use the angles in our triangle. Good. Okay, nice, Awami. So technically, 5.5 doubled gives me the 11 in my triangle. So if I say double this angle, I do get the 11 degrees. That's an angle in my triangle, and exactly what Kani kind of just spoke to now. We want to be using angles in my triangle. Otherwise, I'm not going to get the k value. Now, this is, like I said, for me, I don't know why, my brain struggles to wrap my head around this. This is now where we just need to be mindful of the fact that 5.5 is not in my triangle. So I just need to be careful. So what we know is that if we took cos 11, okay, we could go and expand that according to my double angle formula, and you could use any, because remember, cos double angles, we'll just quickly scroll back to our formula sheet. Cos double angles, there's 3 of them. So you can obviously use any one that you want, but I would bear in mind that I've already found sine of 11 and cos of 11. And of those 2 ratios, so there's sine 11. Oh, no, there's cos 11, there's sine 11. Of those 2, cos is definitely the easier ratio, k versus square root 1 minus k squared. So I'm going to pick the cos double angle ratio that just deals with cos. So I'm going to deal with this double angle over there, just because it's the easier ratio. Let me be clear, you can pick any of them. It'll be absolutely fine, but make your lives easier. So we could expand this to be 2 cos squared of 5.5 degrees minus 1. And so what we need to bear in mind is, because my double angle is the angle in my triangle, I need to work backwards now to get to this cos of 55.5 degrees. So essentially what I'm now doing is I'm solving an equation without actually doing a general solution. So I want cos 55 degrees. That means I need to get rid of this -1, this 2, and the squared. So we're using inverse operations to essentially isolate the cos 5.5 degrees. We know that cos 11 is k. So we're introducing that k variable that we want, and we're going to use our inverse operations now. So the first inverse operation I'm going to do is I'm going to add 1 on both sides. So now I've got k plus 1 is equal to 2 cos squared 55.5 degrees. Divide both sides by 2, so k plus 1 all over 2 is equal to cos squared 5.5 degrees. And then we don't want that squared. We want cos of 5.5. So I need to square root both sides. So cos of 5.5 degrees is equal to the square root of k plus 1 over 2. And now I've got my ratio for cos of 5.5 degrees in terms of k. So my brain struggles with these ones because I always, and it's such a silly thing to forget. I don't know why I forget this. I always forget that cos 11 does actually have a value that I need to substitute in. And then I get myself all turned around with the inverse operations. There's a value for cos 11. Substitute it in and then solve for what it is you're trying to solve for. Rato?
Ma'am, for these questions, do we necessarily have to consider the plus or minus square root rule, or can we just also always assume it's a positive square root?
So in this case, because we're working with an acute angle, we're in quadrant 1, so all of my lengths are positive, so it'll be positive. Generally speaking, in these, you can just assume the positive.
Okay, ma'am. Thank you.
Sure. Right, so guys, I'm just going to do this. I'm going to put in all the mark allocations, as I said earlier, but just so you can see everything. So I can't remember who else now. I think it's Connie, but I can't remember. You get a mark in the first question for doing your Pythagoras calculation and a mark for your answer. In the second question, also worth 2 marks, you get a mark for expanding your double angle formulae, sorry. And then you get a mark for your answer. In 513, it's 3 marks now. So getting the compound angle formulae. Substituting in your special angles. And then your final answer. And then 514, also 3 marks. Getting your double angle formulae. Again, you would have, any of the double angles for cos that you would have chosen would have been fine. I just picked the one that was easier. Getting a mark for your simplification. So doing essentially all your inverse operations. And then a final mark for your answer. So 3, 6, 7, 8, 9, 10. 10 marks of your 50 straight off the bat we've gotten. So what is that? 20% we've gotten in the first question of trig, hopefully. Now, guys, again, I don't think these are hard questions, but I do think they're hard questions if we don't make the connections in terms of what it is that we have and what it is that we can work with. So once again, look out for, and if you want to take a screenshot, if you want to wait to take a screenshot, that's cool. So look out for your reductions. Look out for your double angles. We love a double angle in these questions. Look out for your compound angles using special angles. And I want to say as a last resort, so I'll put a little star here, co-ratios. That's not how you spell result, is it? And the reason I'm saying this is because if you've drawn your triangle, having that 79 degrees is essentially the co-ratio. So you shouldn't ever need to use a co-ratio if you have drawn your triangle properly. Then you should be absolutely fine. But these 3, reductions, double angles, compound angles, particularly using the special angles, look out for those. Okay, that is what you should have in your head when you get questions like this. Yes, like I said, if you want to still screenshot with all of that, that's cool. And then we'll have a look at our next type of question, which is simplifying an expression. This is where co-ratios, reduction formulae often come up as well. Sometimes special angles, not a lot, sometimes, but it's usually the reduction and the co-ratio that come up in these questions. Okay, good. And guys, just keep asking questions, okay? I'm not going to stop. I'm going to assume that if you have a question, you ask, but keep asking. Right, so I love these type of questions. I know that not everyone feels that way, and that's absolutely fine. The reason I love these questions is because of those 5 marks, 1 mark is for the answer. All your other marks are for identifying your co-ratios and your reduction formulae. And so even if you mess up somewhere, if you got a reduction and a co-ratio somewhere along the line, that's 2 marks. You're done, all right? So obviously, we would like to get bare minimum 4 out of 5 for this question, but just bear in mind that every co-ratio, every reduction is a mark. So this question says, simplify the following expression without a calculator. Now, guys, when I approach these questions, I just go step by step. Have a general overall look at what you're dealing with, but go step by step. So when I say have an overall look at what you're dealing with, there's a couple things I'm going to point out and then we'll deal with them in a second. So the first thing I want you to bear in mind is that there are 2 angles that are just acute angles. We've got sine 25 and we've got cos 65. Now, the way that you know you're going to work with a co-ratio is if those 2 angles add up to 90 degrees, they're a co-ratio pair. So 25 plus 65 is 90. That's a co-ratio. Okay, so that's the first thing that I noticed. The second thing that I noticed is the fact that all of my other angles, I say all of my other angles, the other angles that have a variable in is x minus 180, so a singular x, 90 plus x, singular x, but here I've got sine of 2x. That's a double angle. And remember, if we want to simplify or if we want to then do general solution, our angles must be the same. I can't change those x's, but I can change the double angle into a single angle. So those are just things I'm going to bear in my mind as I go along. Right, but let's get into how we actually answer this question. Now, if you aren't super comfortable, and I'm going to do this question as if I wasn't super comfortable with the question, I would leave the co-ratios for last and even the double angle for last. We can come back to those as we work out. I'm first going to deal with what I am comfortable with, which is the reduction, the x minus 180, and the 90 plus. Now, a couple things. What is this? Cos of x minus 180 degrees. I know, according to my Cartesian plane, that my reduction formula is 180 minus theta, not theta minus 180. So that's a bit of a problem for me. The way we fix that problem is, remember, you can add or subtract 360 degrees as many times as you want to an angle and you will still end up in the same place. So I would add 360 degrees to this because this would now give me cos of x plus 180 degrees. And because it's now plus, I can just rearrange those terms. Cos of 180 plus x. And this now takes me into quadrant 3, where the reduction is 180 plus theta. Okay, so just remember, you can add or subtract 360 degrees as many times, and you want to do that when the order is wrong when you're subtracting. So that's the first thing. Second thing is the square. Now, guys, if you really understand squares, great, you don't need to do this. But where we often make silly mistakes with these questions is with the squared term. So remember, the squared term is saying to me that sine of the angle 90 plus x is being squared. That is what sine squared of 90 plus x means. And I always, whenever I see a ratio squared, I write it out with all of these brackets. And the reason being is because depending on what you're squaring, there might be a sine situation, and that's where we often go wrong. So sine of 90 plus x, that is a co-ratio. 90 plus, quadrant 2, so sine is positive there. So this co-ratio actually simplifies to positive cos x. That is still being squared. Cos x times cos x, or cos x squared, is cos squared x. So I have dealt with that squared. Now, why this is important is because often what happens is, if, let's say, for example, you had cos 90 plus x squared, you guys will say, okay, cool, that gives me negative sine x, squared, and you end up leaving it as negative sine squared x. No, if we square a negative, that's positive. So that's why I'm saying rather write it with the brackets, because we don't want to make a silly mistake like that. We want to get our signs right. We want to make sure that we are actually applying our co-ratios and our operations correctly. All right, so now I can go and fill in what I know. Like I said, I'm going to leave the co-ratio situation for now. I know I'm going to have to deal with it. And obviously, if you can deal with it all in one go, awesome. But if you can't, just leave it. We can come back to it. We now have this cos of 180 plus. So 180 plus, quadrant 3. This is where cos is negative. So this becomes times negative cos x. The sine 2x, like I said, I don't want a double angle, so I'm going to have to expand that to 2 sine x cos x. And in my denominator, we now know that that whole sine squared 90 plus x just gives me cos squared x. And then I still have my cos 65 degrees. Okay, this is now where I would deal with my co-ratio. Now, grade 12s again. I don't care which one you change. If you change the sine to a cos or the cos to a sine, it makes absolutely no difference. Personally, I would just choose the first one. Again, it makes no difference. But I would take sine of 25 degrees. Sine of 25 degrees can be written as sine of 90 minus 65 degrees. Because 90 minus 65 gives me 25. That's the same thing. It's just in a co-ratio format. Sine of 90 minus is cos of that angle. So sine 25 can be written as cos 65. And then I obviously have all of my other stuff that I still have worked out. Again, if you can do this all in one go, that's awesome. Do it all in one go. I'm just going step by step so that we understand what we're doing. Right, this is now where we start to simplify. So first things first, cos 65 divided by cos 65. Let's get rid of that. We don't need unnecessary stuff clogging up our space. Let's just get rid of it. I'm now going to multiply what I have in my numerator. So negative cos x times 2 sine x cos x gives me negative 2 sine x cos squared x, because cos times cos, all over cos squared x. And again, simplify. Cos squared x gone. And so what I'm left with here is just negative 2 sine x. And generally speaking, you want to simplify it down to a single trigonometric ratio. Often we do say simplify the following without a calculator to a single trigonometric ratio. All right, so in terms of your mark allocation here, like I say, 4 of the 5 marks are going to be for your reductions and your co-ratios and all of that. So mark for co-ratio, mark for the reduction of x minus 180, a mark for your double angle expansion, that's already 3 of your 5 marks, a mark for in your denominator dealing with that sine squared 90 plus, so that getting the cos squared x, and then a mark for your answer. So like I say, when you get questions like this, and these questions are generally between like 5 and 7 marks, of those marks, 1 of them will be for the answer. The rest will all be for your working out. And so that's why, again, go back to your cast diagram, go back to your Cartesian plane, understand what is happening so that you can simplify appropriately. Lorato?
Ma'am, say now we made a silly mistake, maybe where we just show like simplifications. So if we had included on the side how we got to certain parts of each of our, like our answers, basically.
Like what I've done here.
Yes, ma'am. So would we get like some sort of a mark for carrying it on? Like to basically, you know, when you carry on the same answer, even though it is wrong, you get a mark. Would we also get a mark for that?
So yeah, I mean, we do see a mark, especially if it is, like you say, like a slip. So we call them slips. It was just like a silly thing. So let's say, for example, I don't know, you accidentally changed a sign somewhere or something like that. We do carry on marking. In terms of like the working out, I'm not going to give you marks for like adding the 360 or writing the square out or whatever. But if I can see that you've done it somewhere and then you've just made a silly mistake bringing it over, I could potentially give you a mark there. You obviously won't get full marks, but you could potentially get a mark for your understanding in terms of your methodology. Yeah. All right, guys, I hope we've got screenshots of that. Let's have a look at an identity question. So remember, basic ratio question, simplifying question, proving identity question. Okay, so we have got, I don't really want to read all of this, but I will. Sine x minus cos x over sine x plus cos x minus sine x plus cos x over cos x minus sine x equals -2 tan 2x. Gracious golly. Prove the identity. All right, so when we want to prove identities, grade 12s, we need to work with one side and one side only. So pick the left or the right. Now, generally speaking, we pick the side that is more complicated. The left-hand side is definitely more complicated. I've got multiple terms, fractions. I can kind of see a bit of difference of squares going on there because I've got sine x plus cos, sine x minus cos. There's a lot going on there that I can deal with. So I'm going to work with the left-hand side when I prove this identity. Now, state which side you're working with. I just go left-hand side equals, and then I start going from there. All right, so guys, there's a few ways that you can deal with this question. It's really kind of, it depends what comes to you, right? So in terms of proving identities, there are a few things that we can kind of look out for. First things first, can you apply your tan identity? So tan sine over cos. Can you apply your squared identity? Sine squared plus cos squared equals 1. If you can't do any of those things, we move on to the next thing. Do we have fractions where we can find an LCD? And that's going to be the case here. So can I find an LCD? Can I factorize? Potentially that's going to be useful to me. Or we can throw in double angles, as you can see here, or compound angles. But generally speaking, look out for, can you apply your basic identities, so the tan identity and the square identity? Can you find an LCD, or can you simplify the expression? Can you factorize? Those will be the things to look out for. So if I just look at the left-hand side, because I've got sines and coses everywhere, and I know that I want to eventually get a tan, I know that the only way for me to get this tan is to have sine 2x over cos 2x, because that will simplify to tan 2x. And so always use, as much as you're only going to work with one side of your identity, use the other side as your guide. Okay, so that's what I know I need to somehow get in order to get tan 2x. What that means is I somehow need to go from two terms, so the two fractions, to a single term, i.e. I have to get an LCD. And I somehow need to bring in double angles. Somewhere there needs to be a double angle situation to go from all of these single x's to sine 2x cos 2x. So let's start with an LCD. I'm just going to rewrite. Do I really want to? No, I don't. Let's start with an LCD. So your LCD here, you have got two different, I actually think this might have been a positive 2 tan x, but we'll deal with that in a second. We've got two different denominators. So because it's two terms, we're just going to cross multiply the situation over here. Now, this is not going to look nice. Please understand that proving identities, it's not going to look nice for a little bit. We have sine x minus cos x times the LCD cos x minus sine x. That's just first fraction. Minus sine x plus cos x times the LCD sine x plus cos x. Okay. That is all over, we'll get it right at some point, my LCD here. Sine x plus cos x times cos x minus sine x. Great. So like I say, it doesn't look nice. Not enjoying this in any shape, sense, or form, but it's going to get nicer. Now I need to expand everything. So I need to distribute. Now, guys, I try and do this as like to get the simplified answer immediately. I get that that might be lazy, and that's cool. But we're going to distribute everything. So sine x times cos x, and then negative cos x times negative sine x. Those are both positive sine x cos x. So I end up with 2 sine x cos x. Cos x times cos x, negative cos squared x. And then the sine x times the sine x, negative sine x squared. Come on. There we go. Negative sine squared x. So that's distributing my first term. Then I've got the minus. I need to keep that there because I'll distribute again. Distribute everything. So sine squared x plus 2 cos x. 2 sine x cos x. I suppose it doesn't really matter. It'll get there in the end. Come on. There we go. 2 sine x cos x plus cos squared x all over my LCD. Now my LCD, again, I need to be thinking I have to end up with a cos 2x in that denominator. And I know that one of my cos double angles is cos squared x minus sine squared x. So let's maybe distribute this out and see what we get. So I distribute my denominator. It's not going to be great. But because I've got different signs, I should be thinking difference of squares. So cos x times cos x is cos squared x. Sine x times minus sine squared x. And then the other terms cancel out. So sine x times cos x, positive. Negative sine x times cos x, negative. Those two cancel out. So this in the denominator is actually the cos double angle formula. That's great. I'm getting to where I want to be. We just got to sort out this numerator. So what we're going to do is we're going to distribute in that negative. Obviously, again, grade 12s, if you can see which terms are going to cancel, that's absolutely fine. Just start canceling away to your heart's content. However, I'm going to distribute in this negative, so it becomes minus sine squared x, minus 2 sine x cos x, minus cos squared x. So we're looking squared. I do apologize, but it's fine. Now, again, also in your denominator, if you know immediately that's going to be your cos double angle, you can change it, which I'm actually going to do just to save myself some emotional turmoil. Come on. So cos 2x. If you have no idea what I'm talking about, look at this expression. Cos squared x minus sine squared x. If we have a look at our formula sheet, cos squared minus sine squared. That is the cos double angle, or one of the cos double angle formulae. All right, so in our numerator, let's get rid of some nonsense. 2 sine x cos x minus 2 sine x cos x, gone. Don't want it anymore. I then have this beautiful situation going on up here where I've got minus 2 cos squared x minus 2 sine squared x all over cos 2x. And now we need to go and simplify further. So can I not add and subtract some things here? Let me just make sure that I have everything that I need. This is going to be interesting. This is not how I ended up doing it, but let's see what happens. So we've got minus 2 as a common factor, cos squared x plus sine squared x all over cos 2x. Which does not give us what we want. I've done something wrong. Sorry, grade 12. I did this earlier. Like, this is on my 3rd, 4th time doing it. And now I'm just losing my mind. See, this is why proving identities is so gross. That is negative. That is negative. That's positive. That's positive. Negative, negative. Okay, so I have not lost my mind there. What did I do earlier? This is all right. Oh, girl. No? Okay. I think I've been a bit silly in this distribution. Just let's check this. You can check it with me. So no, I'm not losing my mind. Sin x times cos x, that becomes positive, which it is. Yo, great tools. I feel your pain. This is right. Okay, I can multiply, so that's a good sign. I did this perfectly fine earlier. Like, can't tell you why I'm like having a brain fart right now. Sin x times cos x minus sin x. That's right. This is right. That is correct. That is correct. That is correct. That has to change. Oh, this is going to hurt my brain. Because the cos squareds and the sine squareds should all cancel out. So what am I doing? That is so silly. It's somewhere here. Must be multiplied though. Trigger's going to be the death of me. Hi. This was the longest June exam. Let's see if we can problem solve this in the last 8. I promise you if I can't figure this out, this is just because I've... So, Kazimla, we could work with the right-hand side. The problem is, though, if we go right-hand side, the only thing I can do here is say minus 2 times sine 2x over cos 2x. And then I would have to expand my double angles, which we could do. It's just in a case of which double angle am I working with here, which, I mean, you definitely could do this. So yeah, if you wanted to give that a try, absolutely. I just feel like I'm just being like incredibly stupid right now. Because I know my mistake is in my distribution. I've done something silly in distribution, what that is. But because like we can definitely try it. Yeah, and we're probably going to have to do this on Wednesday in any case. Owami, tell me, what have I done wrong?
Hi, ma'am. Can you hear me?
I can?
On the memo, it's a positive cos squared x, and on what you've written, it's a negative cos squared x. I don't know if that's...
So this is my problem. This one and this one, they should both be positive. Now, when I did this earlier, I got positives. Why I'm getting negatives now, can't tell you. So what... What's tripping me up here is that they've also swapped the denominator. Can't swap that without changing the sign to a plus. Okay, guys, I'm going to be honest. I think I know where I've gone wrong here. And it's really stupid. I think it's literally that plus sign, because I think this memo is wrong. Because that should be a plus if you're going to swap that. So this is my own stupidity. So it's not, because then it's still not going to work, because then you're not going to cancel out things. I feel like there was a mistake somewhere and no one corrected the mistake. So I think that this denominator should have been the other way around. Oh no. Okay, technology also doesn't want me to do it. This denominator should have actually been the other way around and should have been sine x minus cos x, not cos x minus sine x, despite the question paper saying that. Ratel?
Ma'am, for the two that you highlighted, the negative cos 2x, negative cos squared x, and the negative sine squared x, wouldn't it be correct because it's a negative and a positive being multiplied together? Even though
so they have to be negative.
Yes, even though I get on the memo they swapped it, maybe that is why.
So look here, this is the original question. I genuinely think that this is actually an error in the question paper, and obviously no one said errata. So this is the original question, where it's cos x minus sine x, exactly what we have here. But we cannot go from cos x minus sine x to sine x minus cos x without changing this sign over here. That has to then become plus. Because if we're going to change the order, we have to change the sign. So I think it is an errata. I'm going to see if I can find out. But I think it's an errata in the question. It should have been the other way around. Because then it works out perfectly and then it's beautiful. So we've had a time here. Great for maths, hey? Right, grade 12s. It's 2 minutes past 7 and clearly, identities don't want to work. We will do another identity on Wednesday.